Hey, as promised, now I'm going to do a slightly more complicated example with KVL and KCL. So I'm going to draw out a circuit and then I'm going to solve it for you. Okay, what I have here are four circuit elements. I have an independent voltage source, a resistor, a dependent current source, and you can tell because there's an arrow, so this is a current source, and I have it drawn in this diamond, which indicates it's dependent. And then I have another resistor over here. In this particular problem, I'm going to write down a few pieces of information that we do know, and then I'm going to pose a specific question. We're going to solve for a specific quantity in this circuit. So let me write some things out. We have Vs, a source voltage at this independent voltage source. We're going to say that this is a 10 ohm resistor, and there's some voltage across it, Vx. So this is some voltage that we don't know, denoted Vx. And there's some current through this element as well, and we'll label it Ix. This dependent current source is going to have a certain relationship with the current Ix. So we're going to say that the current here is A, some constant, times Ix, where Ix is another current in this circuit, this one that I labeled here. And A is a constant that I'm just going to label down here. We're just going to say that we know it in this case, and A equals 0.5, and the units here will be amps per amps, which really isn't units at all, so it's just a constant, and it's saying that that this current is 1/2 of whatever Ix is. That's all that means. And then the last thing is we're going to say we have this last resistance here. We're going to call this 5 ohms. And there's some current flowing through it. We'll call it IY. And the question, okay, one more piece of information that we know in this problem is the voltage across this resistor here is 15 volts. Now the question, I know it seems like I've written out a lot of stuff, but just if you look through one piece at a time, I'm just labeling voltages and currents and resistances, and if you think about it, there's something that we don't know here. Well, there's a few things we don't know. We don't know Ix, we don't know this exact current from the dependent source, so we don't really know Ix, we don't know Vx, we don't know Iy, and if you noticed, I didn't actually give you the source voltage. So the question around this circuit is going to be, what is Vs? What is the source voltage? Given the information that we do have about this circuit, we have the values of two resistors, we have the voltage across one resistor, and then we have this relationship that the dependent current source has with another part of the circuit, and the value, this constant of proportionality that it has. So given that information, we actually can solve this circuit, so to speak. We can determine what Vs is. Now I'm going to walk through that step by step. So the first thing that I would do analyzing this problem is just ask yourself, okay, what's being asked of me? I'm being asked to find a voltage. So it's probably natural that you might want to use Kirchhoff's voltage law as a starting point. And if you think about it, we have Vs here, and with this polarity indicated by its plus minus terminals. So I'm going to employ Kirchhoff's voltage law here and write an expression for Vs in terms of some other voltages in this circuit. So using KVL, I'm going to write an equation here, and if you remember, what KVL says is that the voltages as you travel around a loop will sum to 0. And I'm going to choose a convention here that as I walk around, when I move from the positive to the minus of a voltage, I'm going to say I'm going to count that positively. And when I move from minus to plus, I'm going to count that negatively. And so the cool thing about KVL is that it applies to any loop, right? So I know, if think about how many loops there are in this circuit. There's really 3. There's this small loop that involves the source, the resistor, and this current source. So there's a small loop here. There's a loop that involves these two elements, the current source and the resistor here. But there's actually a larger loop that, and this is what most people miss, If you ignore, you can ignore this current source and realize there's actually a larger loop that goes around the entire circuit. So there's three. There's two little loops and there's one big loop. And the loop that I'm going to analyze right now is the bigger loop. And KVL is valid for any loop in any circuit, whether it's one of these small loops or it's a bigger loop that might contain other elements inside. As long as you have a closed loop, a closed path, KVL does apply. So using KVL, if I count these, let's say we have plus Vx. I keep moving, and then I get to this plus 15 volts, and I keep moving, and then I get to this Vs, except it's minus Vs, and then I get back to my starting point. So what I really have is plus Vx plus 15 minus Vs equals 0, right? So this two positive voltages and this negative voltage equals 0, and I can just rewrite that in equivalent algebraic form. I can say that Vs equals Vx plus 15. So maybe I don't know if that's too much, but if I'm skipping a step there that you don't realize, so the explicit formulation for KVL that I wrote out is I go around and count them. I say that Vx plus 15 minus Vs equals 0. So that's the explicit formulation of KVL that I described as you walk around in some voltages with the correct polarity and they sum to 0. So then all I did was just move Vs to one side so it looks a little bit nicer. So we know that Vs equals Vx plus 15, right? So those are equivalent. The total voltage Vs appears as the sum of Vx and 15. So that's great. To figure out Vs, all we have to do is figure out Vx. The only problem being we don't know it. But if you notice, this is where we use other information that we have in this problem. We know the resistance. We know that there's 10 ohms here. So what's the most natural way to figure out a voltage across a resistor? Well, what's the current through it? If you know the current through this resistor, then you automatically know the voltage. So let's see if we can figure out the current. The next thing I want to do is think about, like, well, how can we determine Ix? Well, we could try employing Kirchhoff's current law. And I think the most natural thing to do would be to try and relate this current to the other currents in the circuit, because we have information about these other currents based on their relationships with a dependent source or this current's relationship with this resistance. So if we have a little bit of information about these currents and we can relate them to this unknown current, then I think you'd be surprised that we can start pulling information and building up knowledge about this current. So that's what we're going to do. I'm going to write an expression for KCL, and I'm going to look at this node right here that I'm kind of circling with this dotted line. And remember, KCL says that the sum of the currents entering a node is 0. Or equivalently, you could say the sum of the currents leaving a node is 0. And when it comes to the pluses and minuses, just like with the voltage, you have to assign your own convention or reference polarity. So I'm going to say that any current entering this node is positive, and any current leaving the node is negative. So in this case, I can say that Ix plus AIX minus IY equals 0. Okay, and that's essentially what I'm saying, is that IY, well, since IY is leaving that node, it's equivalent to me saying that minus IY is entering the node. So therefore I write that IX entering plus AIX entering minus IY entering equals 0. And then just like I did before, I'll simplify this a little bit and just say that IX plus AIX equals IY. And if you look at that, that intuitively makes a lot of sense. You have two currents coming in and one current leaving. So this current must be the sum of these two, and that's all this expression means. And now we get to do a little bit of nifty algebra. But first, I guess you want to notice, okay, well, what's IY? We actually know it. because we have this information about this resistance and this voltage. And so we know via Ohm's law, that I equals V over R. So a little bit of quick math here, 15 divided by 5, that's going to be 3. So in this case, we know that IY equals 3 amps. So then, and we also remember we have knowledge about this constant A. It was given to us as 1/2 or 0.5. So with a little bit of algebra here, we can just factor out this IX, and we have 1 plus 1/2 equals 3. And so if you now solve this, then we have that therefore IX equals 2 amps. Okay, fantastic. Because now that we know IX, we actually know Vx. And another way to write Ohm's law would be that V equals I times R. So given that we know IX is 2 amps, and we know this resistance to be 10 ohms, then we can easily say, so we'll say Vx equals Ix times R equals 2 times 10. So Vx equals 20 volts. And awesome. Now all that's left to do is plug this into our initial algebraic sum for Vs. Therefore, Vs equals 20 plus 15 equals 35 volts. Awesome. And that's the solution to our initial question, given this information that we had about this circuit. And we were asked, okay, what's the source voltage, Vs? And there we go, it's 35 volts. And so you could go back and verify this if you wanted, and that's probably a good exercise. Once, you can use KVL and KCL to analyze what are given to you as complete circuits. If I had just started this problem with giving you all the information, all the resistances, all the voltages, all the currents, you could just use KVL and KCL and verify that all the sums give you 0. It's a great tool to check your work. If you ever find that this doesn't hold up, then you have wrong information. You have incorrect values for a voltage or a current or a resistance somewhere. Another thing you could do, like I discussed in the last video, is you could go around and measure that. You could make sure that power is conserved. So you can think about, okay, well, how much power is sourced by all the sources combined, and how much power is consumed by all the passive elements combined, and then make sure that those two things are equal and opposite magnitude, so that you have a total negative power that's sourced and then a total positive power that's consumed, and they should be equal, or if you summed them together it would be 0. And so there's a lot of ways you can check your work here, and this is a more complicated example than I discussed in the last video, but still a simple circuit relatively. So I think this is a good one though, because people do get tripped up by the dependent sources sometimes. So just work through this example a few times on your own, or you can even contrive your own circuits and see what you have to do to make them work. And so I think I'm not exactly sure what I'm going to do next. I may just continue on with examples and maybe get a little bit more and more complex. I think that's probably a good idea, to do a few more circuit examples before I introduce more information about circuit elements, because we've only scratched the surface there, and there's more tools you can use to incorporate analysis of resistances in your circuits. So with that in mind, I hope this was helpful, and thanks for watching. Let me know if there's anything I can do to improve this experience, and other than that, have a great day.